Today, we're going to have a look at how we can design tokenizers, or more specifically, a BERT tokenizer for low resource languages. So, when I say low resource language, I mean a language where we don't really have that much data and there is not already a tokenizer or transformer model out there built for that specific language. Now, there are transform models and tokenizers for a lot or even most languages, but there's still a lot of languages that are, well, simply less common and get less attention than something like English or Chinese. So you may find if you're working one of these languages, there are very few models out there, or maybe no models out there. So that's what we're going to focus on today. We are going to more specifically focus on building a tokenizer, and in the future we're going to do more of this as well, more models and so on. But we're going to focus on building a tokenizer for the Dhivehi language. Now, Dhivehi is the language of the Maldives, so the Maldives Islands in the Indian Ocean. I'm sure a lot of you will probably know them, but they're very beautiful islands, incredibly amazing weather, and generally I would not usually think of the Maldives and NLP in the same context, but there are a lot of people that do. And in particular, there's a guy called Ashraq, or Ismail Ashraq, and we've been speaking a lot about NLP, and through that I've been made aware of how difficult it is to actually build models for languages where there is not much attention out there already. So what we decided to do is kind of team up and try and put together some transform models for the Dhivehi language. And the first step to that is obviously the tokenizer. You need a tokenizer before you build anything else. So there are a few hurdles that we kind of need to overcome when we're building these models. So there are zero, well, not zero, there are some pre-trained models for Dhivehi, but they're not necessarily that useful for what we want to apply them to. And you may think, okay, there's those multilingual models with hundreds of languages included. Now, from at least what I've seen, all of them miss Dhivehi. Another thing that is difficult with Dhivehi and other low resource languages is actually finding text data. Now, labeled data is practically impossible for a lot of these languages, but unlabeled, unstructured data, maybe that's a bit more reasonable. You can build a web scraper and scrape loads of text from whichever language you are using, the websites in that language, on the internet. And that is what Ashraq has done to get the data set that we're using today. And as well as that, another really difficult thing is that Dhivehi uses a very unique writing system that is known as Thaana. And Thaana looks really cool and is definitely very unique and beautiful, but it's not really very well supported even by those multilingual language models. As you can see here, it looks really cool. You're also going from right to left, which is quite interesting. Everything's also in the same case. There's no uppercase or lowercase, which is, again, quite interesting, I think. So there's a lot of unique properties with this language that we need to deal with. And from what I've seen, there are no current tokenizers which actually support these characters. So we really do need a tokenizer. First step is getting data. So like I said before, Ashraq went and did the hard part and took or scraped a load of Dhivehi text from the Dhivehi internet. And he managed to put together 16 or more than 16 million samples of Dhivehi paragraphs and sentences. Now, obviously, there are going to be little things in there that we maybe don't want, but for the most part, it's actually very good. So step number one is downloading the Dhivehi corpus from Ashraq. And you can see here, so it's hosted over here on Hugging Face, so we can use the datasets library to go ahead and actually get that data, which is pretty useful. So we just do pip install if you don't have it already, datasets. Okay, now once that's installed, we can go ahead and we just write this. So we are going to Ashraq's Dhivehi Corpus, and we are taking the train data split from that corpus. Now, it's fairly big. Like I said, it's more than 60 million samples. So what you can do, if you don't want to load it all at once, you can set streaming equals true. And what that will do is create an iterable object, which you can see down here. And that means we can perform a for loop and iterate through the data one sample at a time and not download the full thing in one go. We just download each sample as we loop through the whole list. So you can see here, that's what I've done. So the row here in DB train, so we're going through the train split. We're just printing one row at a time. And again, you can see that really cool Dhivehi text in here. Now, there's just 3 samples here, so it's very simple. We just have almost like a dictionary. We have text, and then we have the Dhivehi text following it. So that is it. All I've done here. So I'm creating a generator object because later on, when we are loading this data into the tokenizer, we're going to be loading it in as a generator, and that generator will expect us to load the text in almost like lines. So we'll expect to iterate through and just receive the text. It will not expect to receive a dictionary which contains the key text which actually leads to the text. It expects just this here. Okay? Nothing else. So what I've done is create a generator object here. And you don't need a numerator. I'm not sure why that's there. So we remove that. And all this does is iterates through each row and extracts the text from each row. So it's literally going through and extracting this and nothing else. So now when we actually use that, that's what we get. So here we're using this DB text function or generator. We are using the exact same code we did before. We're just printing the row. You see now we don't get a dictionary, we get just a plain text, which is what we want. Now, that will be fed into our tokenizer train from iterator method. Now that's kind of skipping ahead a bit. So let's go back and take a look at where this tokenizer is coming from in the first place. Okay, so we have in our tokenizer, we have a few different steps. So let's say we have the tokenizer. It's not just a tokenizer. There are different components or sub-processes. The very first is the normalization. Now, this is optional. You don't need to do this, but it's useful. So given maybe we have something like we have these 2 words. So this is specifically European languages here, but we have C and C. Now, these are pretty similar, and a lot of people may actually use these interchangeably, although they, as far as I know, are actually different words. But people may use them interchangeably. And if we would expect that, then we can use something called NFKD, Unicode Normalization, to actually take both of these and create the same word, which would just be SI. And this is particularly useful if you have weird characters. So, for example, rather than the letter, F, like this, you see people on social media using like the weird ones, not like, well, kind of like this. It's all these weird characters and stuff. But basically what they mean is an F. And because we're people, we can understand that's what they're talking about. But a machine learning model is not going to see those as the same thing because they have different Unicode patterns. So what we do is use NFKD Unicode normalization, and we convert them to being the same thing. So that can be quite useful. Another very useful thing is you can also lowercase within your normalization step. So that's also useful. Now, like I said before, with Dhivehi, you don't have uppercase and lowercase, so it's not really necessary for that. But if we do have, for example, English text in our data at any point, it's probably better we normalize it or lowercase it, because that means we will create less non-Dhivehi tokens. So, for example, if we have the word hello, and we also have the word hello like this. Now, without lowercasing, these may become two separate tokens and take up more space in our tokenizer vocabulary, where we only really want to keep Dhivehi characters or words. So what we can do is lowercase that, and that reduces the likelihood of getting like duplicate lowercase and uppercase non-Dhivehi characters in there. So that's another thing we will do. So let me remove all of this. So we are going to lowercase and also use NFKD. Okay, so that's the first component. The next component after that is pre-tokenization. Now, pre-tokenization is, well, a tokenization step that happens before we actually tokenize. So what I mean by that, so pre-tokenize, let's say we have a string, hello world. It's probably easiest. Now, what this is going to do is just split this into very simple tokens. So we might say anything with a space will get split, or anything with space in between it will get split, and maybe punctuation as well will get split. So then we would end up with the token hello. A list from this. We get hello, we get world, and we also get this exclamation mark. It's messy, but I think that makes sense. So that is the pre-tokenization step. And then after that, we actually have the model or the tokenizer itself. Now, write model. Now, this is where you have something like a WordPiece tokenizer, which is what we're going to use. Now, WordPiece is the tokenizer that BERT uses, and later on we're going to be using BERT models, so that's why I've stuck with WordPiece. And what this will do is it will take all of the tokens we've created and it will merge them into the most or the largest logical components that I can think of. So this isn't a very good example of the hello world, but let's say we have being, maybe. Yeah, being, we can do that. So being, for BERT specifically, this would probably get split into something like B, and then a subword token, which is always prefixed by these double hashtag symbol, and that would be ing. So we get two tokens from that because it's a BERT, or the BERT WordPiece tokenizer is a subword tokenizer. So it doesn't split every word, like hello would probably just be hello, but it will split some words that it sees as being more relevant if you split them, which can be useful. For example, if you had like it snowed, it is snowing, and snow or snowboarding, you would get snow in all of those, and then you'd get boarding or board and ing. You get ing for snowing and snow ed for snowed. So that can be quite useful to find patterns in the the words or subwords. The next step is post-processing. So post-processing, and this is where we would add any special tokens to our text. So BERT specifically would use something like a what's called a classified token, followed by, let's say, hello world, followed by a separator token. Then you probably have padding tokens and all of these different things. So we're adding in any special tokens there. And we're also going to create different tensors. So we will have an input IDs tensor, which will be the ID or integer values that represent each one of these word tokens or subword tokens. We have token type IDs, which is useful when you have sentence pairs. And you will also have a attention mask tensor, which tells BERT or the transform model which tokens to actually pay attention to. For example, ignore any padding tokens. So, I mean, they're the main components of a tokenizer, but there is also another which we will, I think, almost always add at least, which is a decoder. So when your model outputs, let's say it outputs a word prediction, so it is predicting, you've masked the word, let's say here we've covered hello, and we said, BERT, what is that word? And BERT is trying to tell us hello, but BERT doesn't know the string hello. It just knows token ID values. So it's going to give us, it's going to say, this is my prediction is the number 3. And obviously we're like, okay, great. I don't know what number 3 means. So we need a decoder to take that number 3 and translate that into something more readable for us, which would be hello. Okay. And that's what a decoder is for. So obviously we don't need it for the input into BERT, but we do need it if we want to understand the output from BERT. So that's our tokenizer components. That's reasonably high level, but let's go into the code and we'll have a look at how at least how we've implemented that for our BERT WordPiece tokenizer. So in this, we are using the Hugging Face Tokenizers library, which is very good, and would definitely recommend you do the same. Otherwise, this can be very difficult. Now, to install this, you would just pip install Tokenizers. There's nothing more to it than that. And what I've done here is imported everything that we're going to be using. Now, you can see a few of the components I mentioned earlier. So we have decoders, the models, which is the tokenizer itself, normalizers, the pre-tokenizers, and the post-processors as well. Further on, we have these other 2 classes, and we'll get to them soon, so I'll explain them later. Now, first thing we want to do is actually, we're not going 1, 2, 3, 4 like I said before, because then we would be initializing the normalization step first. Instead, what we actually do is we initialize the tokenizer, and the main component of that tokenizer is the model. So in this case, WordPiece. So we initialize that using tokenizer here. So you see up here, we have tokenizer. This is just a wrapper so that we create a Hugging Face tokenizers object, and in there we need to pass the type of tokenizer that we're using, and we are taking that from models up here, and we're using WordPiece. Now in here we also have the unknown token, so you need to specify that. So that's where your tokenizer, if it sees a word it doesn't know, it will place this. Okay, it will put UNK rather than just leaving it empty or not understanding. This is like the only thing it can put there instead of raising an error or something. So we put that in there. Now, after we have initialized that tokenizer instance, we need to set the tokenizer attributes, which are going to relate to the components that we listed just a moment ago. So here we set the normalizer attribute in our tokenizer, which we just initialized. And we're setting that equal to normalizer's sequence. So there's a sequence of normalization steps here, and we are using the lowercase first, so we lowercase everything, and then we are using NFKD, Unicode normalization. That's all there is for that. So we've set the normalization step, then we do the pre-tokenization step. Now, pre-tokenization is where we're splitting our string into tokens, so words or punctuation. Now, the simplest way to do this is we use this white space tokenizer. So all that does is splits on either white space or on punctuation, like commas or exclamation marks or something like that. So that's it. We've set out pre-tokenizer. And then we have this. So this was another part that we didn't mention. So we imported this trainers. So if we come up here, we imported it here. Now, trainers is basically the method that or function that we'll be using to train or control the training process of our tokenizer. And all we're doing here is we're using a WordPiece trainer, because we have a WordPiece tokenizer model. We are setting the vocabulary size, so that's the maximum number of tokens that our tokenizer will contain. And then we also need to set any special tokens. So we already set one earlier, but we need to make sure that is included. So with special tokens, we probably won't see them, or we hopefully won't see them in our input text. So, or the text that we'll be training on. So what we do is we insert them now beforehand. Okay, so we have this unknown token, padding token, classified token, separated token, and masking token. Then here we set the min frequency, so the minimum number of times we need to see a token to add it to the vocabulary. And then we also, earlier on, you saw we had the subwords in our WordPiece tokenizer. Here we're just setting the prefix that identifies those. So it's just the two symbols there. Now, at this point, we're back to the start. We're downloading Dhivehi Corpus again. We already covered it, so we can skip that. We already have the Dhivehi Corpus, and we are storing it in the generated DB text here. And then that's where we get onto our training step. So the reason that we put DB, or we create this DB text generator, is because we're training from iterator here, which expects to receive lines of text. So we have DB text, and then the trainer is equal to the trainer. So the trainer we defined just up here. So that controls the training process. And that's it. So this, once you run that, that will run through all of the text in your DB text generator and train to the specifications you've set in your trainer object. We can check, so the tokenizer, we can get the vocab size. We set that earlier, and we can see, yes, it's 30,000. So as we would expect. Now, before, when I showed you that list, there were 5 steps, and we've covered 1, which is normalization, 2, pre-tokenization, and 3, which would be our actual tokenization model. Now, after that, we train the tokenizer, so we train using those first 3 steps or components. And then we still need to define the next step, which is the post-processing step. Now, the first thing we do is we get our classifier ID, so the integer value that represents CLS and the integer value that represents SEP. We get both of those, and we use this processing or processes template processing method to create this here, which is looks quite messy, but if you take a look at this here. So we have the one input at the top and we have the two inputs at the bottom. So when you are feeding just a single sentence into your BERT model, what's going to happen is, looking at code, we are going to use this format. So we're going to have our CLS token followed by A, which is sentence 1, followed by the separator token. Now, back to the image, we have on the bottom, we have two sentences. Now, if we feed those into BERT, they need to be understood as separate sentences to BERT, or separate maybe question and context, for example. Now, in that case, back to our code, we would format it as a CLS token, followed by sentence A, the first one, followed by a separator token, separate the two sentences, and finally, we would have sentence B after that. And then again, we do finish with a separator token again. Now, another thing that's different here is that we have this :1 for the pair. Now, that's for the token type IDs array. So token type IDs tells BERT where we have sentence A and sentence B. Now, in the case of a single sentence, everything in token type IDs is equal to 0. So it's just all 0, 0, and 0. The alternative, where we have two sentences, is that sentence A is going to be 0 and everything related to sentence B is going to be 1. It's as simple as that. And then we need to specify the special tokens that we're using here. So we have CLS and we're specifying it again here and mapping that to the actual token ID integer. So that's the post-processing step. That's all sorted. We don't need to do anything else with that now. And we can move on to, so after this, our tokenizer would feed the input IDs that it creates into the model. And then we would move on to the decoder step. So after BERT has finished processing whatever it's processing, it's going to output you a number, like a word prediction maybe. It's going to give you a token ID, and we need to know, okay, how do we decode that into something we can understand? And maybe it gives us a load of token IDs. And what we need to do is say, okay, we're using a WordPiece tokenizer and we're going to decode from WordPiece. And we also, because we're using WordPiece, there's this prefix. This is already set by default, by the way, but I'm just putting it in there in case you want to use a different prefix, although I wouldn't recommend it, but if you have the reason to, you can change that. So that's our tokenizer. And that's it. So we've initialized, or we created our tokenizer, and after that we move on to saving it into a format that is most useful to us. So I think most of us, when we are using a tokenizer model, we're probably going to use Hugging Face transformers, not Hugging Face tokenizers, because they are two different libraries. And when we load a tokenizer with Hugging Face transformers, we tend to use this pre-trained tokenizer or pre-trained tokenizer fast class. Now, what we can do is save our tokenizer into the format that is compatible with Hugging Face transformers and compatible with this class specifically. And to do that, we first actually initialize the tokenizer, the Hugging Face tokenizer, using this class. So we are using pre-trained tokenizer fast, and if you've used this before in Hugging Face transformers, we usually write from pre-trained and we load a model from here, so like based on case. This time we're not using that, we're not using any methods, we're just initializing the object directly. We pass the tokenizer to tokenizer object. Then we also have the unknown token, padding token, and the other special tokens in there as well. Okay, so that is ready for us to save. It's in the correct format now. So all we do is take full tokenizer, which we've initialized up here, and we save it as a pre-trained model. And what I'm doing here is saving it to the BERT-based DV directory. And once that's saved, it's going to save these 3 files here. And from there, we can actually just load it from pre-trained like we normally would. Now, just one thing, when we load from pre-trained, normally we probably are going to be loading from the Hugging Face models hub. In this case, we're not. We're loading from a local directory. So in some cases, maybe you have this in a different directory. So you would write something like your path here, which would go to a different directory, and then you would have your model directory there. Okay, so just be aware of that, and then we can test our tokenizer with some Dhivehi text, and we see, okay, cool, this is Dhivehi text. No idea what any of it means, but it looks great. And from that, we get 3 tensors. So we have the input IDs tensor, which are the 2 represents, I think, the CLS token, and the 3 here would represent our separator token, the 2 special tokens. Everything in between is Dhivehi, or the punctuation, like these brackets, open and closing brackets, this comma, or something else. And then we have token type IDs. Now we only have 1 sentence here, so it's just sentence A, all of that should be 0. And then we have the attention mass tensor as well. In this case, we don't have any padding, not adding padding, so the attention mass should just be 1. And that's it. Our tokenizer is actually ready. Now, if you do want to go ahead and actually load this tokenizer directly rather than going through all of this, you can. You just write James Callum and load it like this, because this is on the Hugging Face models hub. We have a model, and this also includes a BERT model as well. So you have the BERT model, which you can load, and also the tokenizer. So that is it for this guide or walkthrough to building a BERT WordPiece tokenizer for a low resource, or a language which does not have any currently supported tokenizer. So I hope this has been useful. As I said, the tokenizer is really just the first step in what we hope will be a greater way to support the Dhivehi language, and particularly the AI community over there, in what they are building and doing by putting together a few BERT models that are fine-tuned or built for specific or different purposes. And like I said, this is the very first step in that. So I hope it's all been very useful. Thank you very much for watching, and I will see you in the next one. Bye.